Right, so as I said, or if I haven't said, right, this is the final chapter. Right, sorry. This is the final little bit of AQA AS Physics Unit 1. This is the very last thing, or bits of information, a pen's gone walkies, that you need to know. So we're nearly there, don't worry. You know, you can sit down, have your cup of tea, and we'll go through this last bit. Now, in my previous video, if you bothered to watch it, I talked about many things, but I talked about oscilloscopes. I did mention it. I said we're going to cover it in this tutorial, which by the name of the YouTube video and what you've typed in YouTube, that's what we're going to be doing today. So, an oscilloscope. Let's maybe asking me. Well, I know what an oscilloscope is. It's one of them boxes with like a wave on it. Well, there's not a really definition. It may. I'm going to rub this off, so just to get you to know if you don't get by that brilliant explanation of what you may have seen like an oscilloscope looks like. So you've got like a little display here, and I'm not going to centimetre it, but because it's a small display, and it'll have something like that, and you'll have two buttons here, and then you'll have two leads here going in from whatever you're testing, and that will give you the X and the Y PD or sensitivity, depending which one it is. So, as I said, if you can see that, great. If you can't, never mind. But it's going. So, that you should know. Well, yeah, that's an oscilloscope. Now, oscilloscopes tend to be quite boxy old things. Something you might see in the 1980s, and you know, maybe not like a square thing as that. But it's quite chunky, and you go, well, what is actually behind that? What is in this area here? Because modern day electronics are quite thin. You know, you can have something like that. Well, to answer that question, that's what we're going to be talking about for the remainder of this tutorial there. Let me just pick up a book. Sorry, just give me a second. Yeah, so just making sure you can see that. So that is the main bit more light there. Yeah, changing lighting all the time. It's pretty darn good. This you don't get that on any other revision video. So oscilloscopes, right? So you know, I was going to say, well, what's in that big boxy thing at the back? Well, you know, you've got your battery or your power, depending on how your oscilloscope's powered. So I'm going to draw a cell here, which is connected to a filament bulb and an anode. Obviously, I'm going to label this in a minute. It goes back there. It's got another anode here. You've got a battery here, plus mine, and that is the complete circuit. And then comes out a little bit, and you've got two planes. You've got to me, I'll just draw it and I'll explain what bits I've drawn. So I've labelled it here. Just give me a second, guys, don't worry. Doing the physics in a minute. They just called it X and Y plates. Yeah, these are just plates. So these are what we call the Y plates. Why is that? Well, they alter the PD in the vertical Y direction. You may have seen a graph, you've got X and Y, you know, it's just the same thing. So X plates, and we've got our fluorescent screen. So how does this produce to something like that what we see? Well, if we've got anodes here, so you probably label that. Hopefully you get that's a filament. We've got a steady emission of electrons here. As an anode is a positively charged electrode, emission of electrons, so it can emit electrons basically. And then if this is no PDs going through the Y plates or the X plates, we get focused spot of light. I'm just gonna. That looks a bit wrong. You got a focused spot of light there. Now, what can we deduce from this? Well, that is where the electrons are hitting the fluorescent screen, and it's fluorescent, so we can see that given point there. Let me just double check you can still see that. I mean, obviously I could put it up and then everyone would be like, what's that? Hopefully you can see that. Should be okay. So, yeah. Well, that is an oscilloscope, and if it's direct like that, then what we'll have on this screen, I'll just draw the screen of just have like a straight line going through its two things there. And that'd be your oscilloscope for that one. Obviously I'm going to rub this off when I find the rubber, which I've got in there. So that'd be your basic oscilloscope we have there. I'll just get rid of this. Right. So hopefully I can get rid of the word fluorescent screen just to make a bit more room for me. Alright, okay, so yeah, get rid of that as well. This is crazy, I've just put the rubber in. Crazy. So, the electrons are being emitted, assuming we've put no potential difference through either the X plates or the Y plates, then we have a focus dot in a straight line. That's what you're given on your oscilloscope. So if we want to change the Y, so Y is vertical, X is horizontal, that's what the PD affects it. So if we increase the X plates, it's going to move more horizontally. However, if we increase the Y plates, the potential, when I say increase Y plates, what I mean, or increase the X plates, what I mean is increase potential difference in these plates. It's basically a sort of circuit if you think of it like that. Is that how they draw it? Just make sure I've drawn it right. Yeah. So, if we move the X plates, it's going to, so we increase potential difference of the X plates. We'll rub this off. It's going to, so we increase it, it's going to go that way. It goes, yeah, so it would cause, so if we're looking at it in terms of the screen, so the X plates are connected to the time base circuit in the oscilloscope. So if we increase the X plates, what we do is increase the horizontal distance of, so it would become something like this. Not very good, but never mind. However, if we increase the Y, then this would be deflected. So if we increase the Y, then this would be deflected. It'd go, I don't know, something like that. And then that would go something like that. So we'd have, so I just put that X, and that'd be Y, changing Y, changing X. We'd have a lot bigger things. Not necessarily further apart, but I'm just giving an example there. So if we want to increase the vertical height, sort of the amplitude of these waves, then we increase the potential difference in the Y plates, which are these two. If we want to increase the sort of frequency sort of thing, and we increase the X plates potential difference. See if we anything else we need to put. Just anything on the oscilloscope more. So the PD displayed is a PD of the Y plates. So I'm just looking for extra facts I've missed out. Facts. Okay, so to measure the peak PD, so to peak PD, we use this in the root mean square value when we were calculating that of the other circuits we talked about before. I'm just going to say the root mean square value, if you don't already know it, it's the value, the root mean square value of an alternating current, which is what we're looking at, is the value of the direct current that will give the same heating effect as the as the alternating current would through the same resistor. That's just, I have gone over that in the other video, so if you don't understand what I've just said there, you need to go back and look over physics. So, when an alternating current, sorry, we were talking about PD. So to increase the peak PD, which is that one. Oh no, wait, sorry, we talked about P. Sorry, just give me a second. Sorry about that, guys. Okay. So, as we were saying, you can change the X, sort of, if you change the X, increase the potential lift of the X plate, you sort of increase frequency because there's more cycles per second. If you want to increase the sort of amplitude, you increase the potential difference in Y plates. So how can we use this to relate it to the actual basic sort of display of a oscilloscope? So let's draw, hopefully I can get rid of this, just give you a minute to pause it if you haven't done already, which I'd be surprised. Ouch. And we'll rub it off, so I'll just give you a minute. Right, hopefully you've done that. Rub it off. And I'm going to just explain, we've practically done the course now, I've just need to go over ways of measuring ultrasonic waves. And yeah, just go over the rest of this oscilloscope stuff, making sure there's nothing else, sorry. So, we've got our, I'm going to draw it bigger this time, yeah, ready guys. Yeah. So, even I managed to fail a big one. Okay, so I'll just draw a few centimetres, grids even. Just give me a second. I should have done this before. Right. Okay, so that's our centimetre grid, that's our display. If you can think of it like that. So I'm going to get a different colour when I find one. Well, we'll go with green. Does this green work? No, this green doesn't work. This isn't very good preparation, I admit, but never mind. For God's sake. Right, this pen's got to work. You just put your pens around. Right, that'll go. Okay, so imagine we've got this is the 0 PD, and no, it's not exactly accurate. Oh, that's alright actually. So we've got a wave, might go like that. Just making sure I'm doing this right. 2, 2. Oh wait, that's 1. Right, this is really bad, I have to admit. Never mind. For sake, I can't draw. Right. I'm just trying to make it as accurate as I can. Right, that is very good. But you get the gist. So that is 0. That's our wave that we've got on our oscilloscope. This is the Y sensitivity. I'll just put Y, and it's our X sensitivity. X. Now these are centimetre, generally are centimetre grids, or like 0.8 centimetres, or whatever you might be interested in. So we've got the amplitude here, and the amplitude gives us our peak value for the potential difference. Is it? Yeah, the peak potential difference. So we'll label this peak potential difference. Now you can't just simply measure it, put a ruler up the screen of your oscilloscope, got it in the end, because it's going to be in sort of what's it called? Y gain. Why is that? Right, so you've got something called the Y gain, and now that's basically saying for every centimetre square, hopefully what that is, what is the potential difference going up? So each square could represent, I don't know, 2 volts per centimetre. So if each square is 1 centimetre, then It's 2.5 volts if I've thought of that right. So what you do is that's perfectly 2. Well, I've tried to make it perfectly 2. So say for a Y gain, now Y gain is basically for each one we go up how many volts or potential difference, so we're increasing it by the same thing, but Y gain. And say it's, I don't know, 5 volts per centimetre. 5 volts Cm minus 1, just means 5 volts per centimetre. And our amplitude is, I don't know, let's say, to do an easy one, 2 centimetres. There's a 1 centimetre block and we're perfectly at 2. So to get the amplitude, or the peak potential difference, we times, you can probably guess this, work this out, by timesing the amplitude by the Y gain, or the Y gain by the amplitude. So 5 volts per centimetre times 2 equals 10 volts. The centimetres cancel out and we're left with 10 volts. And that's our peak potential difference. Now if you wanted to know the root mean square of the potential difference, you just do 10 volts over root 2, and then that would give you the root mean squared value. But I don't think we need to work that out one. And I think that's all you need to know. But the frequency, if you want to work out the frequency, because the time period is 1 over frequency equals t, you just swap t and f around, so you've got 1 over time period equals frequency. I've just done that very quick in the corner because it's just a rearranging of an equation you should already know. So that it may ask you, well, what's the frequency? It's just 1 over the time period. The time period is the amount of time it takes for one whole cycle to pass, or one whole wavelength sort of thing on the screen, how it appears. So just to go over that again, if you want to change, I'm going to go over it from the start, so I will go before this bit. Just a quick recap on, we've not finished this little video, but just a quick recap on what we've done so far. So the anode fires the electrons at the screen. A fluorescent screen shows a bright light where the electrons hit. If you want to increase the Y sensitivity, you increase the potential difference in the Y plates. However, if you want to increase the sort of grouping it together, you increase potential difference of the X plates, and that increases the X sensitivity. And to measure the potential difference, or PD, you times the amplitude distance by the Y gain, and then that will give you the peak potential difference. And 1 over the frequency equals the time period, rearrange that, and you get 1 over the time period equals the frequency. Hopefully that's starting to make a bit of sense now. Right, so I did say we'd be going on to actually, one sec, I will go over just direct current, but it'll only take a moment. Sorry, I didn't think I'd need to do this, but it is very, very simple. So I'm only going to spend a few minutes on it of your life. It's up to you whether you watch it or not. So we've got a oscilloscope. Now I'm going to be really lazy, not draw the grid on there. But say we've got just because it'll just be a straight line, that's why. So we've got 0 potential difference at this direct current. So there's no current going through it basically, because there's no, because V equals IR, there's no current. 0 times whatever resistor you may have, it's going to give you potential difference of 0, crazily enough. But if we increase that, we can increase the voltage. This gives us 1 plus 1. Now, all it does is simply move it up or move it down. Similarly what you're doing with the amplitude of a alternating current. And that is the direct current version. So the same thing applies if you want to make the peak current, or peak potential difference, you times the Y gain, which is the sort of how much voltage each centimetre represents, centimetre box, and you times that by the distance between these 2 points, and yeah, that will give you the peak potential difference, which is constant for a direct current as it doesn't change. I think that's all we need to know on the direct current. As I said, there's not much to it, so that's why I didn't draw a grid, because it's only taken a few seconds really. But still, it's life you're never going to get back, I'm afraid. Anyway, so measuring the speed of an ultrasound. Now, I don't think this is particularly important, so if you've got bored of the video, you can switch off, but I would advise you just to go through and watch it if this is watching it for the first time. So, if you stayed with us, thanks. If you haven't, you know, shouldn't be listening to this. It's been a long day, okay? Don't, you know. So, let's draw our thing. When I say thing, that's the oscilloscope. And you've got your, is it the oscilloscope? Yeah, that is not very good. Just the whole thing. So we'll draw our thing. I'm using thing quite a lot, but sorry, I'm really bad at drawing these. Never mind. So that's the wavefront. Oh great, wait, sorry. It's ultrasonic again. It's not a standard one. Oh dear, long day. Yeah, that's the right one. I was drawing an alternating current. This is not an alternating current, it's an ultrasonic wave. So it means it's very fast. So, how can we measure this? Well, you've got the Y. You only use the Y plate for this, because it's only going to go up. It's not going to. Well, just use a Y plate. Just acknowledging that. So you've got your transmitter. So I'll just put T, transmitter, not time period. This obviously sends out the ultrasonic wave. And you've got your receiver. I'll just put R. And this goes back into the Y input. Just put Y, because we're measuring the potential difference, which is shown on the Y plate. So basically the same sort of thing. You times, if this is, say, we've got a distance in centimetres, we could just call this D in centimetres. So it's not very neat, but never mind. Trying to lose the will to live. I'm sure you are too. So if the pulse is 3, this is, just go through an example I've got in the book here, just to make sure I don't mess it up. So if this is 3.5 centimetres, I'll just put it at 3.5. Then, if we work out the time-based control, now time-based control is, does it say? It's just how far it travels per second, sort of thing. And it's 0.2 metres. Basically, all you need to know is you times the distance by the time-based control. I'm not 100% sure on the time-based control, but it's just, that's what you do. So if you're working out the speed, you just times the distance by the time control. So it's just speed equals distance times time. It's a very simple formula. So, except instead of time, it's time control. So I'll just put that V, speed, equals D times time control. Sort of similar thing to the Y gain sort of idea. I know that's not very a good explanation of the oscilloscope measuring the speed of an ultrasonic wave, but you just need to know your times distance by the time control, and that gives you that on the screen, the oscilloscope. Now, just forgive me. Right. So I'll just go over it again, everything. The first bit of it, we talked about the oscilloscope and what it actually looks like inside, and we talked about the anode emitting the electrons, the Y plates turning the YPD up and down. The XPD is sort of X sensitivity is denoted by the X sensitivity. The X plates connect to the time-based control. The Y plates show the PD. So if the X plates increase the potential difference across the X plates, the frequency is increased because the bars are a lot closer together on the screen, and it's we should get that really. You should. So if your potential difference across the X plates increase, you increase the sort of frequency, if you like, think of it that way. If you increase the potential difference in the Y plates, you increase potential difference. So it's like you increase the Y gain sort of thing. Well, you don't increase the Y gain, but you increase the peak frequency, peak potential difference even. One day. And then was there anything before we go on to that? Oh yeah, before we go on to direct current actually, should we just make sure I've not missed anything? Oh yeah, to measure the peak voltage, got it right in the end, you times the amplitude distance by the Y gain, which is the amount like each per centimetre. Oh yeah, you saw that was pretty good. So the Y gain is how much each centimetre block is in terms of voltage. So you can times that by the distance in centimetres obviously, and that will give you the peak potential difference, the peak height of the wave. And I say wave because it isn't a wave, that's just how it's shown in terms of X and Y sensitivity on the screen of the oscilloscope. So just to go over that again, the anode fires the electrons. Y sensitivity is the Y plates increase Y potential difference. You increase the sort of amplitude of the wave. If you increase the X potential difference in the X plates, you increase sort of the frequency of what it looks like. To measure the amplitude or the max voltage, you times the amplitude distance on the screen by the by the Y gain, which is the percent each centimetre how much it holds sort of thing in terms of voltages, or potential difference even. And direct current is just a line, same sort of thing, you times it by the Y gain distance, but it's just a straight line because it's direct current, it's not altering direction in terms of plus and minus voltage. And then we looked at the speed of ultrasound transmitter times the distance by the time control, and that gets you the speed of the ultrasonic wave. That is Unit 1 AQA AS Physics done. I thank you. So yeah, that's oscilloscope. So oscilloscopes, anode emits the electrons. The Y sensitivity is denoted by the Y plates, increase potential difference, increase the amplitude of the wave, increase the X potential difference across the X plates, which is that little box thing we talked about. You increase the frequency if you look at it like that, and it moves the position of the spot of the light. So we can say that the light is the displacement of the light spot is proportional to the alteration in PD. And then the max voltage or max potential difference is you times the amplitude by the Y gain, or how much each centimetre represents in terms of voltages, and then so the time period, one of the time periods is frequency, and then we looked at speed of ultrasonic waves and direct current, just a straight line because it's in altered direction, because direct current, one direction, which is bad, don't say that. And you move it up and down, same sort of thing, times this by the Y gain, and the speed of an ultrasonic wave, you times the distance by the time control, and that gives you the speed of the ultrasonic wave. Now, well, that's pretty much all you need to know. Oh, that was a lot. So we'll see you in the next video.